So zeros to enhance bandwidth. Zero as bandwidth enhancers. So one of the way to increase the bandwidth is to add zero in the transfer function of out impedance of the amplifier by using circuits like shunt peaking, shunt series peaking, and shunt and double series peaking. Shunt peaked amplifier circuit is shown in the figure. Shunt peaked amplifier and model of shunt peaked amplifier. The transfer function V out by I in is the out impedance of the RLC network. The gain of a purely resistive loaded CS amplifier is proportional to GM/RL. As frequency increases, the capacitor's impedance decreases. The addition of an inductance in series with the load resistor provides an impedance component that increases the frequency, that is, it introduces a zero. Hmm. As frequency increases, the capacitor's impedance decreases. The addition of an inductance in series with the load resistor provides an impedance component that increases with frequency. Okay. Next, the the output in Z on Z for X is equal to SL plus R is parallel to 1 by SC is equal to R of S of L by R plus 1 by S square LC plus SRC plus 1 into E. The magnitude of Z of J omega is equal to R of square root of omega L by R whole square plus 1 by 1 minus omega square LC whole square plus omega RC square. As frequency increases, a term in the numerator increases. The Z of X also increases. As frequency increases, a term in the numerator increases. The Z of X also increases. As frequency decreases, the term 1 minus omega square LC will also increase the Z of X. As Z of X increases, the bandwidth increases. The problem with the above equation, choice of L, we introduce a factor M defined as the ratio of the RC and LR and L by R time constants. Small m is equal to RC by L by R. Then Z of X is equal to SL plus R is parallel to 1 by SC, that is equal to R of tau s plus 1 by S square tau square m plus S tau m plus 1, where tau is equal to L by R. For a given value of R and C, there is no single optimum value of L that we can choose. The problem is to choose a value of M that leads to some desired behavior. The maximum bandwidth will obtain when M is equal to square root of 2, that is equal to 1.41, which extends the bandwidth to a value about 1.85 times as large as the uncompensated bandwidth. Unfortunately, this choice of M leads to nearly a 20% peak in the frequency response. Condition: maximum bandwidth condition M is equal to R square C by L. This is the formula. And normalized bandwidth range, maximum bandwidth approximately equal to 1.41 and bandwidth is approximately equal to 1.85. Maximally flat frequency response and no shunt peaking. Okay, the values are like this. Shunt and double series peaked amplifier. Introduction of L3 delays the diversion of current into rest of the network, indicates the transistor drives only its output capacitance for some time. So, indicates the transistor drives only its output capacitance for some time. Rise time increases, bandwidth increases. Okay, next. The design of amplifiers at high frequencies involves more detailed considerations than at lower frequencies. At lower frequencies, the method of open circuit time constants is a powerful, intuitive aid in the design of high bandwidth amplifiers. On minimizing various RC products, it leads one to a relatively narrow set of options to improve bandwidth. For example, we may choose to distribute the gain among several stages or alter bias points all in an effort to reduce effective resistances. These actions usually involve an increase in power or complexity, and at extremes of bandwidth, such increases may be costly. Generally, consideration of the problem of designing amplifiers with large gain bandwidth products, it is possible to construct networks in which gain trades off more with the delay, allowing much greater flexibility in constructing amplifiers with large gain bandwidth products. Okay, the high frequency amplifiers are the shunt series amplifier, tuned amplifier, and cascade amplifiers. An alternative approach to the design of broadband amplifiers is to use negative feedback. One broadband circuit that employs a negative feedback is the shunt series amplifier. It uses both shunt and series feedback. It maintains constant input and output impedances over a broad frequency range. Okay, the shunt series amplifier is shown in the figure. Shunt series amplifier. Here RS, RIN, RF, ROut, R1, R1 and RL are presented in shunt series amplifier. The amplifier core consists of RF, R1 and the transistor and the transistor. Let us assume that R1 is large. R1 provides series feedback, RL provides shunt feedback, and that reduces the input and output resistance and helps to increase the bandwidth. The voltage gain of the amplifier from the gate to the drain is approximately minus RL by R1. The input resistance Rin is given Miller effect as Rin is equal to Rf by 1 minus Av. That is approximately equal to Rf by 1 plus RL by R1. Now to compute the output resistance, apply a test voltage source to the drain node and again take the ratio of Vtest to Itest. Rout is equal to Rf plus Rs by 1 plus Rs by R1 is approximately equal to Rf by 1 plus Rs by R1. If both the RL and Rs should be equal to R, then the equation may be written as Rout is approximately equal to Rin approximately equal to Rf by 1 plus R by R1, that is approximately equal to Rf by 1 minus Av. Design of shunt series amplifiers. Okay, once the gate to drain gain and input resistance are known, the overall gain is trivially found from the voltage divider relationship. The effective transconductance of a common source amplifier with source degeneration is Gm comma effective is equal to Gm by 1 plus Gm into R1. The effective transconductance is approximately 1 by R1 as long as Gm into R1 is much larger than unity. Applying a test voltage from gate to ground causes a drain current to flow through both the load and feedback resistors. The output voltage Vout is equal to minus Gm gamma effective V test, that is RF RL by RF plus RL plus V test RL by RF plus RL. The gain of the amplifier AV is equal to Vout by V test, that is equal to minus RL by R1 into 1 by 1 plus 1 by Gm into R1 into 1 by 1 plus RL by RF into 1 minus 1 by Gm comma effective RF. The terms in brackets are ideally unity.